It's a critical look at Leonard Susskind's book, The Black Hole War. And this isn't just about black holes themselves, it's more about how complex physics gets communicated. And specifically, where the source material suggests the author's own philosophy might muddy the waters a bit.
That's right. The notes really set out a mission for us. Can we tease apart let's say, the core physics concepts, general relativity, singularities, all that tricky stuff from how Susskind presents them? We need to figure out if his style actually helps explain these ideas, or if maybe it sometimes gets in the way, especially for, anyone trying to get up to speed.
Yeah, we're going to zero in on what the critique calls out as the big conceptual hurdles, those moments where maybe our everyday intuition just crashes against what relativity predicts.
And we'll definitely keep an eye on the math. The source is quite concerned about places where the explanations might rely on shortcuts or assumptions that, well, aren't made totally clear. That's a big deal for popular science writing.
Okay, let's dive into part one then. The critique really goes after what it calls the author's philosophical or personal distractions. It flags a specific claim, page 242, where Susskind says our difficulty visualizing some physics comes down to our evolutionary past. He says mental pictures have more to do with limitations imposed by our evolutionary past.
Right, and the first red flag for the reviewer is the lack of backup. It's a huge claim about how our brains evolved, but the source says, hang on, where's the research? No citations listed for that specific point. So the critique suggests it's less a scientific point and more, perhaps, leaning on ideology, evolutionary psychology, maybe, to sidestep a tricky physics explanation.
Feels a bit like an explanatory shortcut, maybe, but the critique hits harder on Susskind's praise for Darwin. Our notes highlight phrases like Darwin's masterstroke, ejecting God from science, replacing creation's magic with laws of probability and chemistry.
Yeah, the source sees this as, well, it uses the phrase embarrassing prostration towards Darwin. The argument isn't really anti-Darwin. It's that this framing treats Darwinism like a kind of belief system, a religion for atheists. And the source questions whether relying on a 150-year-old idea, one that doesn't fully answer modern biology questions like life's origin, is the right foundation for arguments in modern theoretical physics.
That's a pretty sharp interpretation of why he might bring Darwin into it. Does the critique offer any reason why an author would put these personal views in a physics book?
The source basically argues it's a mistake in addressing a wide audience. Injecting personal ideology makes the reader judge the author, subjectively, rather than focusing on the actual physics being presented. It distracts.
And speaking of personal angles, the source is also critical of how Susskind talks about Stephen Hawking. It points out the strangeness of listing Hawking as a hero right alongside Nelson Mandela and Moby Dick, and then spending a lot of time attacking his scientific stance.
Exactly. There's a specific bit the source quotes where Susskind talks about Hawking's influence, comparing it almost to a Pied Piper leading a false crusade against quantum mechanics. Okay. The critique suggests this crosses the line from scientific debate into something more personal, maybe resentment, and asks, why put all this personal, almost theological tension in a book about the information paradox? The takeaway from the source is pretty clear. Writers aiming for a broad audience should probably keep their personality a bit more in the background. Let the science do the talking.
Okay, let's shift gears. From the communication style to the physics concepts themselves, and specifically the analogies used, here's where it gets really interesting. Let's talk about the equivalence principle. That accelerating elevator analogy for gravity, it's everywhere. What's the specific issue the source finds?
The issue is geometry, essentially. In the idealized accelerating elevator, the floor pushes up on you, and those lines of force are perfectly parallel. Everywhere on the floor feels the same upward push. But real gravity, especially from something compact like a star or a planet, pulls towards the center. So the lines of force aren't parallel, they converge.
Okay, so if I'm in this huge hypothetical elevator moving upwards fast, and I drop two balls, say, a foot apart,
They'll accelerate down towards the floor perfectly parallel and land exactly a foot apart. The force field is uniform across the floor. But if you do that near Earth, drop two balls a foot apart, gravity pulls them both towards the Earth's center. They actually land less than a foot apart because their paths converge slightly.
That's a subtle point, but it matters, right? Because that convergence is the basis of tidal forces, the very thing that stretches objects near a black hole.
Precisely. The elevator analogy works fine for understanding the feeling of gravity as acceleration, but it completely misses the tidal aspect, the stretching and squeezing. It only really works if you imagine a one-dimensional elevator, just a single line. For someone new to this, it builds a mental picture that doesn't quite fit with things like spaghettification later on.
We run into similar visualization issues with string theory concepts, don't we? Like the usual picture of rolled up dimensions, the garden hose idea, a long straight dimension, and tiny circular ones wrapped around it.
Yeah, and the logical trap there, according to the source, is thinking about the space needed to see the analogy itself. To actually visualize a 2D surface, the host surface, curled up in a 3D space,
Yeah.
you need those 3 dimensions, length, width, depth, laid out flat, so to speak. You can't really picture it if you only have 2 dimensions available.
Which then makes you wonder, okay, if visualizing one curled dimension needs 3 flat ones, how many flat dimensions would you need to properly picture the 3 flat ones we know, plus the 6 or 7 extra dimensions string theory often talks about being curled up? It gets dizzying.
And the source uses this to suggest that sometimes theoretical physics can feel like it's explaining itself with models that, well, assume a reality bigger than the one they're trying to describe. It becomes a bit self-referential.
Okay, let's get to the main event. Black holes themselves. The source really pushes on this question. Are these things truly physical, or are they mostly mathematical constructs?
Well, when we talk of the singularity, the point at the center, we're definitely deep in the mass world. The idea is that all the mass crushes down to a point with 0 volume, infinite density. Why? Because the mathematical models of gravity, like general relativity, don't have any force built in that's strong enough to stop the collapse once you get past nuclear forces. So the math predicts this endpoint.
Yeah.
A huge mass in basically a single mathematical point, a pixel of space.
And that leads to the Schwarzschild radius, RS, the event horizon. It comes from general relativity, but the notes highlight something weird. A calculation using old-school classical physics gets the same answer. The source calls this disquieting.
It is definitely confusing if you're trying to learn this stuff, because it takes formulas that shouldn't really apply and gets the right answer. It uses the classical kinetic energy formula, K equals 1/2 mv squared, and the classical gravitational potential energy, P equals gmm over r. It sets them equal, basically saying kinetic energy needed to escape equals potential energy binding it. Then it puts in C the speed of light for v and solves for r.
But wait, the thing trying to escape is light, a photon. Photons have 0 rest mass. How can you use formulas with M for mass?
That's the crux of it. The mass of the escaping particle, the photon in this case, appears on both sides of the equation. So mathematically, it just cancels out, poof, it's gone. And you're left with the correct formula for RS. The source finds this deeply unsatisfying, maybe even misleading. Why should classical particle equations work for a massless photon just because a variable conveniently disappears? It feels like a coincidence, not physics.
So, relying on the math giving the right answer hides the fact that the underlying physical model used was wrong for light.
Pretty much, it suggests that the classical model fails in a way that just happens to give the right number, masking the need for the much more complex machinery of general relativity.
Okay, thinking about these extreme conditions. The source also brings up infinities that pop up in the models. You mentioned infinite density at the singularity. Are there others?
Yes, and these are things the source argues Susskind maybe doesn't grapple with clearly enough for a general reader still thinking in sort of Newtonian terms.
Yeah.
There are 2 big ones tied to the horizon.
Let's take the potential energy one first. What's the issue there?
If nothing, not even light, can escape from inside the horizon, it implies that the energy difference between being just outside and just inside is effectively infinite, like falling into an infinitely deep potential well. Conceptually, this makes everything outside the black hole seem like it has infinite potential energy relative to the singularity. How does nature handle that? How does the math make sense of an entire universe with infinite potential energy? It's baffling for a non-specialist.
Right, that's hard to picture. And the second infinity, you mentioned rotation earlier.
Angular momentum. It has to be conserved.
Yeah.
If you take a spinning star and crush it down towards a point of 0 radius, the singularity, basic physics says its rotation speed has to increase to compensate. As the radius goes to 0, the math says the rotation rate has to go to infinity. You end up needing infinity times 0 to equal whatever the original angular momentum was. Again, it's a mathematical infinity showing up where physical intuition breaks down. And the source connects this to the Asimov principle. The idea, often attributed to Isaac Asimov, that if you truly understand something complex, you should be able to explain it simply without needing these kind of mathematical tricks or paradoxes to paper over the gaps.
Okay, let's step back from the singularity and just look at the horizon from the outside. If we watch someone fall in, what do we actually observe?
Well, thanks to extreme gravity causing time dilation and redshift, we see 2 main effects. First, any light coming from the falling object gets stretched to longer and longer wavelengths, redshifted, eventually becoming undetectable. Second, any clock traveling with the object would appear to tick slower and slower, approaching a complete stop as it nears the horizon. But crucially, we never see it stop or cross, because before it gets there, it fades completely from view due to the infinite redshift.
Okay, so if, from our perspective, nothing ever actually crosses the horizon, then how do black holes get bigger? How do they gain mass? That seems like a paradox.
It's a classic question. And the force discusses Suskind's explanation, which leans heavily on string theory ideas. The conjecture goes something like this. As the object gets infinitesimally close to the horizon, the extreme time dilation causes the object, or maybe the fundamental strings composing it, to effectively spread out across the surface of the horizon. It gets incorporated into the horizon area itself, rather than passing through it in finite time from our viewpoint.
Wow, okay, so it sort of paints itself onto the horizon, and then the added mass makes the horizon itself expand outwards, engulfing that smeared out information.
That's the gist of it. You don't see something fall in, you see the horizon grow. It resolves the observational paradox, but, it requires buying into this picture of strings spreading on a 2D surface, which is pretty speculative stuff.
And the source brings up another consistency challenge here, right, about Hawking radiation.
Yeah, it asks, if time slows down so dramatically for matter approaching the horizon, wouldn't that also slow down the quantum fluctuations, the virtual particle pairs popping in and out of existence that are supposedly responsible for Hawking radiation? If things get smeared out and frozen in time on the horizon, why would quantum fizz still happen at a rate needed for evaporation? It points to the ongoing tension, the difficulty in smoothly merging gravity, general relativity, and quantum field theory.
Okay, now for what the source presents as major mathematical check, this involves the Planck units. What's fascinating here is...
What's fascinating is how these fundamental units, derived from constants G, C, and S, aren't all uniformly fundamental in scale. We often hear Planck length and Planck time, PDT, are the absolute smallest possible scales, and they are incredibly tiny. But then you look at Planck mass, it's about $2 times 10t kilograms.
Which sounds small, but compared to an atom or proton.
It's huge. It's macroscopic, like a tiny grain of dust, maybe a flea's egg, as the source notes. And Planck energy is similarly large on a particle scale, nearly 2 billion joules. So the source asks, are all Planck units really fundamental boundaries? Or are some just artifacts of the constants we started with? It casts doubt on treating them all as equally special.
And this skepticism feeds into the biggest mathematical issue raised in the notes. It concerns Susskind's claim about black hole information. He states that adding one bit of information defined as a photon with a wavelength matching the black hole's radius, $1 increases the event horizon's surface area by exactly 1 Planck area. Hail 2 tals.
Yes, this is a really central claim for the holographic principle and black hole thermodynamics. It connects information, geometry, and quantum gravity. But the source material actually runs the calculation. It uses the standard formulas for black hole mass, radius, energy of a photon, and surface area. And the result? It's way off.
How far off?
Instead of the surface area increasing by $1 PL22, the calculation shows it increases by 32 pi 2 PL22. You run the numbers, 32 pi 2 is about 316. So the area increases by roughly 316 Planck areas, not one.
316 times larger. That's not a small rounding error. That's significant.
It's a massive discrepancy. Right. And what's also interesting, the derivation shows this increase, delta tau, is actually independent of the black hole's mass. The $3 term cancels out. This implies that it takes less energy to add that bit to a larger black hole, but the area increase in Planck units is always this 316 PL22. The source concludes that the claim of 1 bit equals 1 Planck area doesn't seem to follow directly from GR and quantum mechanics. It suggests the result might only work if it's enforced by assumptions within string theory, rather than emerging naturally from the base calculations.
Okay, let's try to pull this all together. We've looked at critiques of the communication style the philosophy brought in. We've examined tricky analogies like the elevator and rolled up dimensions, and we've dived into some core black hole physics issues, the singularity, that weird classical derivation of RS, the infinities, and this major discrepancy in the surface area calculation.
Right. And the thread running through the source material's critique is this feeling of, well, maybe unease. Is the physics being described the actual messy, tangible world? Or is it becoming a highly refined but perhaps self-contained mathematical world? The source insists that the slippery slope between what is supposed and what is known to be real, should never exist, especially in popular science.
So the core tension is between telling a compelling story about physics and maintaining absolute mathematical and conceptual rigor. And the critique argues that in the black hole war, maybe that balance tipped too far towards story, sometimes leaving the rigorous details or even mathematical accuracy, like that factor of 316, behind.
Which leaves us with a final thought for you, listening to this. When you're reading about these incredibly complex, mind-bending topics like black holes, how do you, as someone relying on these popular accounts, get a sense of whether you're exploring validated physical reality? Or are you perhaps just being drawn into what the source might call a very convincing, highly entertaining, but potentially simplified or even flawed math game? How do we tell the difference?